Okay, so now we're going to talk about how to analyze and what to look for in infrared spectroscopy. So I'm going to take you through functional groups one by one, and I've given you all of these written descriptions over here, and these are good and you can read them all. But actually looking at the spectra is really going to help you. Okay, so first of all, we're going to look at hydrocarbons. In hydrocarbons, you have three different kinds of hydrocarbons: alkanes, alkenes, alkynes. We also have aromatics, okay, but I'm going to deal with that separately, okay, not here right now. So CH, which is alkane, okay, this is the backbone of all organic compounds, which means that this is something you're going to see in all IRs, okay, no matter which one you pick up, because everything has CHs, okay, so you're going to see this, which means, and I'm not really saying that you should ignore it all the time, but really we're going to ignore it, okay, for most part, because yeah, you're going to see a CH no matter what, okay, so we're going to have to learn to ignore this in case we want to look at other things, which is really what we need to do, is look at the functional groups, okay. So the functional group is alkene, for example. So in alkene, you will have two frequencies that you will look at. One is, of course, the carbon-carbon double bond, okay? So that's something you're going to look at. And the other frequency you're going to look at is double bond C, and that is connected to a hydrogen, okay? That's the important thing. Here you will see that I'm not giving you the frequency for carbon-carbon, because that frequency for C, single bond C, will fall into the fingerprint region, and we are not looking at the fingerprint region, all right? Okay, so for alkenes, you're looking at these two frequencies, which are here and here. And then alkynes also, you're going to look at two things. So one is going to be the C triple bond C, which appears at about 2100, and this is wave number, okay? And then the other one you're going to look at is the CH, okay? Now remember, the CH bonds, they're coming around 3000. So depending on what kind of carbon you have, this carbon is sp3, right? Single bonded. This carbon is sp2, double bonded. This carbon is triple bonded. So they're going to have different frequencies for the CH bond, okay? And you can see how it is shifting, right? So single bond with the hydrogen, 3000. Double bond with the hydrogen, 3100. Triple bond with the hydrogen, 33. So it's shifting more and more to the left, okay? So remember, triple bonds, double bonds, okay, triple bonds will vibrate at a higher frequency, okay, that's what we learned, okay. If you remember from our previous slide, the C single bond C was here, C double bond C was here, C triple bond C is here. So naturally this also is going to shift, okay, for us. So you can see that the CHs are at a lower frequency, than these double bonds is higher, and triple bond is even higher, okay, for that. So if you remember the trends, it's easier for you to remember things, okay, that's all it is. So I'm just pointing out the trends. The other thing I really want to emphasize here is that when you have an alkene, you're looking for two different things. Now that depends also if your alkene is all substituted or not. So if you had all carbons around it, then you're not going to have the CH stretch, obviously, okay. So it depends on what is around that double bond, okay. The same thing goes with the triple bond. If you have an internal triple bond, you're not going to see that CH stretch, okay. So keep that in mind as you're going through, because this gives you an idea then, is if your double bond or triple bond is terminal or internal, okay. Now internal alkenes can still have hydrogens, okay. So don't take my word like verbatim like that. Okay, let's go on and let's actually see something, right? So here's an alkane. So remember, alkane is all CH, CH, CC. So here you see the fingerprint region, right? And the reason I'm pointing this out is I want you to not look at it, okay? So look over here, and then I'm also going to ask you to ignore this part because this is all CH. Now, when you have an alkane, like this one is hexane, and then you have octane, so on and so forth, the different kinds of alkanes, they will give you a different spectrum, Okay, it's not like they all will look like this. They will give you a different spectrum, and they might be different here in the fingerprint region. For us, our purpose, I generally don't give you any kind of a hydrocarbon to analyze in IR, because how would you? There is nothing characteristic about it. Okay, and what do I mean by characteristic? Let's go on to look at alkene. So if you look at an alkene spectrum, this is, where is it? Here's 1-hexene. So 1-hexene means that you have a terminal alkene. So which means you're looking for C double bond C. Here is the C double bond C. Very sharp, very nice. Okay, around 1600, 1650 or something. Okay, so very nice, sharp peak over here. Now you're also going to see the CH, right? The double bond carbon hydrogen peak, and that is coming on the left side of all of these. Okay, so remember, this is the CH stretch. Now you see the CH stretch also, and now you can see why I'm telling you to ignore this, because every time you're going to see the CH stretch, because all organic compounds have CHs in them, okay? At least the ones that we are going to look at. So, keep that in mind. Focus your attention on what is the important thing here. So what are the important things? For an alkene, the important thing is to look for the C double bond C, and then look for the CH, okay, the double bond CH stretch over here, so that you see a nice singlet kind of, single peak hanging out there. Okay, very good. So that's an alkene. Alkane doesn't have any of that stuff going on. Okay, and again, I don't usually give you alkanes. So here is alkyne, and alkyne, here we have a terminal alkyne. So a terminal alkyne will have the C triple bond C, which is this right here. Remember, double bonds show up here, triple bonds show up around here, which is 2100. And then you will also have the triple bond CH stretch, which also shifted to the left. If you remember, for alkene, it was kind of here, but now for the triple bond, it shifted to the left. Okay, so more energy. It takes more energy to vibrate this. So the key thing here is for triple bond is this peak, right? And then this also. This is for terminal, but you would see this one even if it was internal. Okay, you will not see this one if the alkyne was internal. Now here is another alkyne, and this alkyne is an internal alkyne. So first of all, it is an internal alkyne, so you're not going to see the CH stretch. This alkyne also happens to be a symmetrical alkyne. So because it is symmetrical, you also don't see this carbon triple bond carbon, because if it is symmetrical, it has no dipole moment. Okay, so you don't see anything over here. Does it mean you don't have any alkyne? No, of course not. Okay, so how do you figure this out? Like, if you get this spectrum, this kind of looks like an alkane spectrum, and you might think, oh my God, I have an alkane, I don't have an alkyne. Well, in that case, you have to start looking at other techniques, which is why I was saying that sometimes one spectroscopy technique is not enough. You have to look at others to figure out your structure. So here you might have done some unsaturation test, or you have mass spec, so you know the mass of your compound, or you have the formula from elemental analysis. So there, so you use all of these techniques to figure this out. So you will know that this is not an alkane. This is actually an internal alkyne, which is very symmetrical. Okay, that's why the peaks are not showing up. Again, one thing I want to point out before I move on, look at the CH stretch. It's still here. The CH is all still here. So, we learn to ignore them, okay? Because if you keep focusing on those big peaks, then you will never look at the peaks that you should be looking at. All right, moving on to alcohols and nitrogens. And why are we doing this together is because both of them are similar in the sense that they have hydrogen bonding. Also, they will appear on the left-hand side of the IR. Remember, the OH, all the hydrogen bonds are on the left side, CH, OH, NH, right? So the CH has been coming around 3000, and now OH and NH, they also come around 3500s. Alcohol peak, you cannot miss that, okay? It's going to look really nice and sharp and big, and you'll be able to see that. Amines is a little bit different, okay? Because amines are primary, secondary, and tertiary. You have three kinds of amines. So primary amines is really wonderful. It'll show you two peaks. Why? Because there are two hydrogens in there. Secondary amine has one hydrogen, you will see one peak. Tertiary amine has no hydrogen, so you don't see any peak, right? Because there is no NH in there. So amines is really fantastic in IR, okay? Because you can tell very easily whether you have a primary, secondary, or tertiary amine, okay? And I'm going to show you all the spectra so you can understand how that's working. Okay, so here's an alcohol peak, right? You can't miss that. I mean, like it's just right there on your face telling you, look, I'm alcohol, I'm alcohol. So it's huge, okay? And everything else here, you can ignore all of this, okay? I'm telling you, no fingerprint region, okay? Just stay away from it. I know the labels are there, but just don't look at it, okay? So focus on this region, which is the CH, OH, and H region, the triple bond, the double bond region, okay? So here is the OH, very, very clear, okay? So now whether you have primary alcohol, secondary, tertiary alcohol, it will give you the peak no matter what, okay? One thing I should mention here, okay, and this goes for the alkenes and alkynes also, is that IR does not tell you how many functional groups you have. Like, what I mean by that is, if you have two alcohols, you cannot tell by looking at this peak, okay, that you have a diol or you have a triol. It doesn't tell you how many alcohols. So you need other spectroscopic techniques to figure that you have three alcohols, okay? All the IR will show you is an OH, okay? So you know you have an alcohol, but one or two, we don't know, okay? So that's something, you know, that you have to kind of live with. Okay, so here is a spectrum for an amine. So again, here you can see the peaks over here. Now this peak is not as pretty as the one for alcohol, but it is there, okay? So this one is a secondary amine. So because this is secondary, you have only one of the H's. So only one H means only one peak over here, okay? And again, these are the CH's, so ignore. All right, I thought I'll show you here how the primary, secondary, tertiary are working, okay, for us. So here is a primary amine, this is aniline, and very clearly you can see the two peaks, okay, right there, very nicely, okay. I have cut the spectrum so it doesn't take up all this room. And then here is the one for a secondary amine where you have one hydrogen, very nicely you see the one peak, okay. And it's, you know, you can tell. The size of the peak, okay, again, does not tell you anything about how many amines you have. The only thing about the size is dependent on the hydrogen bonding, okay, because sometimes if you have too much hydrogen bonding going on, things are wider. The peaks are wider, okay, in those cases. So this peak, for example, much clearer than what you saw for secondary amine in the previous slide, okay. So, but this is a secondary amine. And then here is a tertiary amine. Look, nothing, no peak, okay, over there. So this is primary, secondary, tertiary. So amines, as I said, very nice to work in IR because you can clearly tell what kind of amine you're working with. Okay, carbonyl stretching. Carbonyl is going to be the fun one because there are so many carbonyls, right? So there's a ketone, aldehyde, and so on and so forth, okay? And all of these come around the same place, okay? So this is something that you need to kind of understand how they are working, okay? So for example, ketones is very simple. You will see only one peak and that's it. You're done around 1730, 1720. And I will always write this around because things can shift a little bit here and there. Okay. It's not that exactly you will always see it 730. No, things can shift. Okay. So I will always write approximately. Okay. Aldehydes, on the other hand, are a little bit different, okay, because aldehydes are terminal groups, and because they're a terminal, you have the carbonyl group, okay, but you also have this hydrogen. So which means that this is also going to show up. That's how I've written this one. So the double bond is to oxygen and not to carbon. Remember, we saw carbon before. So that's also going to show up, okay, in the IR. So which means for aldehydes, you will see two peaks. For ketones, you will only see one, okay, one for carbonyl. Aldehyde, you will see one for carbonyl and then one for the C double bond H. That you're going to see. So that's something that you have to watch out. That will tell you the difference between an aldehyde and a ketone in case of carbonyls. Okay, now let's go on more to carboxylic acid. When you have a carboxylic acid, you will definitely have the carbonyl peak, but you'll also have an OH peak, okay, because the carboxylic acid is COOH. So you will see an alcohol peak also. Now this is something, it can be a little confusing, okay, because when you have a carboxylic group, that's actually here, I'll write it here. So you have this group. So we never say that you should look at this as, you know, a ketone and this is an alcohol. No, we don't see that. But when the IR is looking at it, it is looking at it as a carbonyl, as an OH. That's what it's looking at, okay? So which means that you have to be able to figure out if this is what you have, or is it carboxylic acid, right? So this one is a ketone and an alcohol. So whether you have a ketone and an alcohol, or do you have a carboxylic acid? So that's something you need to be able to figure out. Again, sometimes you need more than one technique. And then later on, I will show you the spectra for carboxylic acid. You can actually look at the IR and say, yeah, I got carboxylic acid. Okay, you can look at that and you can tell. So, you know, watch out for that when we get to it. Esters are going to be a little bit misleading. Okay, so as I said, these are the hardest ones because they only have the carbonyl, just like a ketone. Okay, so you know, the only thing that will help you here is if you have a molecular formula, right? Ketones only have one oxygen, esters have two oxygens in them. So that can help you, all right, if you have the molecular formula. But otherwise, you'll have to, as I said, you know, you need other techniques then to help you. But ketones and carboxylic esters are going to give you a little bit run in case you don't have any other information. Okay, amides, that's the last carbonyl. Amides are a little bit easier in the sense that their carbonyl is a little bit shifted more to the left, which means higher energy. Sorry, lower energy. Okay, this is higher energy, so it's a little bit lower energy in there, so it has a little shift in there, so that can help you a little bit. The other thing about amides is that you also have the NH. Now the NH here with the amides is very similar to what the amines have. Okay, so if you have an NH2, you will see the two peaks. If you have NHR, so then you will see one peak, and if you have NR2, then you have no hydrogen, so you will not see this peak. Okay, so again, it depends on what kind of nitrogen groups you have, okay, on there to be able to see the hydrogen peak with the nitrogen. I mean, you have to have hydrogen there, right, to see this. But anyhow, so you have the amide, which luckily comes a little bit different from all the other carbonyls, okay? But this is just an introduction. Let's look at some of the spectra and see if we are able to understand, okay? Now, this is just examples, right? You'll have more in assignments. So here's a ketone. Now the nice thing about ketones, and I love looking at carbonyls in IR because they come as such a beautiful peak. Do you remember the one for alkene? And you can go back and look at the one for alkene. It was just like a small peak, okay? But carbonyls, they are just beautiful long peaks. Again, kind of like alcohols in your face telling you, look at me, I'm here, I'm a carbonyl, you know? So here is the carbonyl. Right there, that's a ketone. It could be an ester also, right, depending on what functional groups you're dealing with, so you have to be careful, but you know, that's a ketone. Here is an aldehyde. So an aldehyde, see, you will have the carbonyl, which is right here, and then you will also have the hydrogen, right? So C double bond and then hydrogen, which shows up on this side. Now I want to remind you that when you saw the CH peak from the carbon double bond, okay, so when you saw this peak, when you had a carbon-carbon double bond, this one is a carbon-oxygen double bond, that this peak came around here. The aldehyde peak comes on the right-hand side. I don't know if that helps you. I hope it helps you, okay? But it is supposed to help you. So alkene peaks come on the left side of those CH stretches, and then the aldehyde peaks come on the right-hand side, okay? So those are the things you're looking for when you're looking for an aldehyde. Now, for an aldehyde, you have to look at the CH peak, because if you're not looking at this, it means you have not really identified your aldehyde. Okay, so make sure you're looking at this as well as the carbonyl peak. Okay, there are two peaks involved here. So I gave another example here, and this is for benzaldehyde, and here's another aldehyde, and you can see the peaks over here, okay, that I've highlighted for you. So, you know, it's not that only one aldehyde will show it. Any aldehyde is going to show that. Now, keep your eyes open, because look, this is for ketone, nothing there. Okay, this is acetophenone. So you see the carbonyl, but you don't see anything over here. All right, so that's how aldehydes and ketones work. Now for the carboxylic acid. So I told you how you can tell that you have a carboxylic acid. Look at that massive peak. Huge, okay? It's so wide. Why is it so wide? And that is because of hydrogen bonding, okay? So when I said that you should be able to determine if it is, you know, an alcohol and a ketone versus a carboxylic acid, well, I think you'll be able to tell, okay, because this peak is so wide, okay, that it's telling you right there, I think I'm a carboxylic acid, okay, and then you also have the carbonyl peak in there, okay. Um, there is a disadvantage to having such a wide peak, because if you have such a wide peak, then you hide things underneath it, okay, which are not visible. So that can be a problem sometimes, okay. So for example, if you also had an aldehyde in this compound, you know, this is hexanoic acid, but if there was an aldehyde in there, you may not be able to see those peaks here, okay, because this is so wide in itself, the OH peak. So anyhow, that's how a carboxylic acid looks. And then here's an amide. Okay, so you can see here the carbonyl is shifted a little bit to about 1640. So this is a right shift, not a left shift. This is a right shift. Okay, so that's the carbonyl, but it is nice and big. And then here is the amides. Okay, and this is a primary amide, NH2. So you see two huge peaks over here. And that's, again, it's wide because of hydrogen bonding, but you see nice two peaks telling you that you have a primary amide. The carbon nitrogen, now the only carbon nitrogen that I have over here for you is the nitrile, okay, C triple bond. So you saw C triple bond C, which also appeared in the middle here, which was a small kind of a sharp peak, and then the nitrile, which is C triple bond N, nice long sharp peak, okay, over here. Now the nitrile group is never going to be an internal group, okay, like alkyne was an internal group, so you don't see that peak. Nitrile can never be internal. It's always going to be a terminal group, so you will always see this peak, okay? Make sure you read all of these things, okay? So it helps you. I'm not reading it because, you know, I'm not going to read my PowerPoints. I'm going to explain it. Okay, so aromatics, I just want to mention a few things here, okay, because aromatics are a little bit more complicated because you have to go into the fingerprint region for this, okay. So first of all, when you have a structure for aromatic, benzene has double bonds in it, right? So this is the structure of benzene, so which means you have CH bonds, which means you're going to see something here. You're going to see the double bonds over here that you're going to see. The main thing I want to show you here, okay, from benzene is this peak that I've highlighted for you. And what happens with these peaks, and this is the fingerprint region, this is the only time I will venture into the fingerprint region, is that when you have substitution on the benzene ring, then you start seeing splittings over here. Okay, so if you see a split here in the peak, that tells you that you have a mono substitution going on. Now, we're also going to learn, or you may have already learned about ortho, meta, and then para substitutions. Those ortho, meta, para substitutions, you can tell them by looking at the fingerprint region. I don't have them here for you. We're going to do it in the lab. Okay, so, but you can tell that you have an ortho substitution, a meta substitution, or a para substitution looking at the fingerprint region. Okay, so I will cover that when we meet in the lab, but it's really good. IR is really good for that kind of determination, okay? And that is in the fingerprint region. So here is the summary again, okay, that you've seen before. So here's nitrogen, oxygen, carbon. I put them in the way they appear also. Nitrogen is more on the left side, and then oxygen, carbon, again, remember that's the weight thing. Here's the triple bonds, your double bonds, fingerprint region. And here is a chart. You're most welcome to use this. You can print it out and use this. I have given here for the substitutions, okay, what you see in the fingerprint region, in case you need it. But again, we talk about it in the lab, okay? So all the other ones I've tried to give you as much as possible. And then the ones that I have starred over here, those star means that you're looking for more than one signal. Okay, here I focused only on the carbonyl, but otherwise aldehydes, carboxylic acids, and amides may give you more than one signal. Okay, so you watch out for that as well. So talking about the strength and limitations of IR. So the strength of the IR is, of course, that you can, figure out the functional groups, right? But IR definitely is not enough, okay, to determine the structure. You can see, what we've been looking at. We're looking only at the functional groups. We cannot tell how many carbons you have. As I said, you can't even tell how many OHs you have or how many double bonds you have. You can't tell all of that, okay? So IR is not enough, okay, to tell you about the structure of the compound. The signals, some of the signals may be ambiguous. And again, this goes with your comfort level with the IR. The more you use IR, the better you get at it, the better you understand it, okay? The fingerprint region also. Otherwise, some of those peaks, like, should I be looking at this? Is it anything? Does it mean anything? You kind of have those questions. And that's why I want you to focus on the peaks that I've been helping you to focus on, okay, to help you right now, just to get started. Now, the presence of a functional group is generally a confirmation. Of course, if you see an alcohol, it's an alcohol. How many? We don't know, but there is an alcohol, all right? However, the absence of a signal, it's not a proof, okay, that your functional group is not there, as I showed you with alkyne. So, you can't tell sometimes whether it's there or not, but that may not be for all functional groups. It may be only for some, okay? The best thing about an IR is if you know the IR of any compound, you can compare it, because remember, IR is the fingerprint of any molecule. So you just have to compare it with the database and see if you have your compound or not. Okay, so it's very good for that. IR has really got lots of functions in it. Okay, so here are some worked examples, and these ones are just so that you kind of get an idea of what kind of questions I asked. So here I didn't kind of hide any answers. They're all right there for you. So write the approximate absorption in IRs. So all you have to do is go through the table, look for the functional groups you're looking at, and then just write the approximate frequency, okay, that you will see them. So ketones, very easy, to do. For this one, of course, since it's an amide, you're going to write for carbonyl and also the nitrogens, okay? So go through these and then let me know if you have any issues, but that's kind of how you would answer these kind of questions. Here is another kind of question, is that, okay, there's a reaction going on. What are the changes you will see? Because one of the functions of IR that we use in the lab is to figure out how far the reaction has gone, or at least is it progressing, or do I have any of the starting material left or not? So if you're taking an alkyne and making a ketone out of it, well then, yeah, of course you can tell from IR, because the alkyne peak should disappear and you should get a carbonyl peak, right? So that's what you should write as an answer, that the alkyne peak at blah, blah, blah is going to disappear, and then a peak at around 1700. You see, I said no blah, 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 right? Okay, anyway, so the peak around 1700 should appear, okay, over here. So that's the kind of answer you should give, thoroughly. You don't have to write paragraphs, but at least be thorough in your answer so I know what you're looking for, okay? Now, if you had just written for this answer that a carbonyl peak at 1700 will appear, that also is fine, okay, because there is no carbonyl here, but you have to specify that, okay, for me, that there was no carbonyl in the starting material, so carbonyl in the product is what you're looking for, okay. So similarly here in this reaction, which is a dehydration reaction, the alcohol peak is going to disappear on 3500 and alkenes will appear, okay. So that's what you have to write. Okay, so here we're looking at IRs and we're trying to figure out what functional group we have. So let's look at this one. The first one, oh my God, this is kind of like just telling me right there, I'm a carbonyl, right? So I know there's a carbonyl in there. That's all I can tell because I don't see anything over here. This could be just the CHs, that we see, and we don't look at anything here. So all I can see is a carbonyl. Okay, so that's what I would say. And then if we are looking at the answer, oh no, we have amine also. Okay, but there is no way for us to tell that you had an amine in there because there was nothing over here. Okay, so don't feel bad. Okay, and I'm not feeling bad for myself either because at least I know carbonyl is there. Okay, and that's how I kind of wanted to show you this. Okay, is that how misleading an IR can be in some cases, that unless you had a functional group, or excuse me, unless you had a molecular formula or anything, you would have never guessed that nitrogen was going to be there, right? Because it's not showing there. So it's okay, don't feel so bad. Okay, let's look at this one here. Now, what is this? This is, I don't know about this, but I know what this is, right? This is an alkyne or nitrile, right? But because I'm seeing this long peak over here, this is going to be this very sharp, nice peak for a triple bond carbon hydrogen. Okay, and then this is a triple bond over here. So I think this is an alkyne, and I am right, okay, for that. So focus on the things that you want to see and just go from there, okay? Nothing much more to it. All right, what concepts to learn? Oh my God, just learn how to read IRs pretty much. That's it. There are a lot of uses for IR. IR is used in forensics. It's used in determining structures, your reactions, how they're progressing, so many functions. IR is kind of, most useful technique in organic. Okay, so try to do your best, okay, in remembering all the functional groups and their frequencies.